Hold on. It sure is. So watch your P's and Q's. The whole world's watching. Keep waiting for the one day that anybody is going to open that door and see what we're doing in here. Every other teacher I know has had at least one walk-in by now. One time somebody's walked in to check to see what's going on. My wife has even had people jump in on her Zooms like 3 or 4 times. People from the district and all that. Not one person has ever shown up in here. We could be doing anything, and it would be, well, whatever, it's Shelton. Oh, let's hope it's going okay. But I think it's because we are the farthest from the office. Right? I've always believed that. You have your room farthest from the office, you'll never see anybody from the office. And I don't have any complaints about that. It's kind of why I like being way I am, way over here. Of course, that means that for the last 16 years, they've always popped into 2 classes, 1st and 5th, right? Because the only time they leave their office is at lunch, right? Or at breakfast. So they'll pop in. So every pop and eval has been my first period class, like right when I'm getting ready to start. They just walk right in. I'm like, oh, really? First period? But this year, my first period is really good, though, so that would be solid. All right, so that's a full minute of recording absolute garbage. So I can't wait to post this video. Let's begin. We were going to start with the hill question, and we're going to do the hill question twice because they're excellent examples of where to start with this and where we're going to go that's a little different than what we did last year. So this is like an inverted hill. And I say it like that because, we're going to drive our car into oh, this is a bad car. There's my car. That's the saddest car ever. Oh, none of you can see it. That's good. You probably shouldn't see this. It's terrible. It's terrible. But here you go. There's my inverted car. Whoop. There we go. But I really believe in myself. I believe if I apply myself, there, I'm going to look at the car. So I'm looking right at the car. So how you doing, car? Now, the car is going to drive through. This is a wash. I don't know if anybody lived out west know what a wash is. Nope, nobody? No, bummer. Out west, when there's rains, typically, which is very, very infrequently, but when there's a rain, and the water's coming off the mountains, you're not stopping it. It's going to pick its own pathway through whatever city you've built. So generally, they just build the roads into these washed out areas where the water will run during a rain. It's a lot cheaper than building bridges and trying to navigate the water. And since they don't rain that often, they don't invest their money there. They invest their money in other things that tend to pay off more for those cities. So a wash will be a dugout area of the road that follows a already defined pathway of water. So if you want to get to the other side, just build the road under it. They don't build a bridge. Now that means that yes, when it rains, you can't go through the roadway because typically the water's too high, it'll wash your car away. But if you wait 10 minutes in a place like this, the water's usually gone. It's a desert. So, those 3 or 4 times a year where they get rain, they just figure it's not worth the investment for a bridge. So you'll get these little dugouts in the road like this, and they're called a wash. So in this particular example, what I really want to focus on, again, is we're talking about centripetal acceleration and what that means for our analysis of force. Oh, you got to be kidding me. All right. Whoever you are signing out, that's frustrating. Papa John's Pizza. I sure can. Bye. Jackson Simpkins is signing out. I was surprised you were here again. I was just excited, you came back for, more physics. All right, so here we go. In this example, what I would like you to find is the normal force on the car when it makes it to the bottom. All right, the normal force on the car when it makes it to the bottom. This would be a fairly straightforward AP Physics 1 question. We'll assume the car has a mass of m and that it maintains a constant speed v as it travels through the wash. Now, anybody who's traveled on any kind of road that makes a dip knows exactly what I'm talking about, and you'll know why it works the way it does. So in a problem like this, we do all the same things we've been doing. We consider that at that point, there are a group of forces acting on the object. And you know what they are. We know that there's going to be weight acting on the object. It's in contact with the ground, we hope. So there's going to be a normal force. But here's where you have to start paying more attention. In order for this to travel in a circular path, there has to be an unbalanced force acting on the object, even though the speed might be constant. The velocity is not constant. The velocity is changing for them to travel in a circular path. The roadway is going to have to push up more than the weight in order to keep the car from going in a straight line. If the car had if the car had a normal force that was equal to the weight, the forces would be balanced. And this would have to be the pathway of the car. And we know that's not what we want. So instead, for the car to actually curve, the upwards force has to be greater than the weight. It's not like the weight can change. So for anything that's traveling in a curved path, the forces have to be unbalanced. The trick is for you to recognize how should you frame the problem so that you can do the analysis best. And what I mean by that specifically is how do you structure your coordinate system and your force equations so that you can actually find the answer to the question being asked. Look, we know that the unbalanced force has to be towards the axis of rotation or the center of rotation, which means somewhere up here would be the center of rotation representing the radius of curvature of this path. When we're at the bottom, we know the unbalanced force should be straight upwards towards the center of rotation. So I'm going to set my coordinate system. To be aligned in such a way that the positive direction is towards the center of rotation. And I would strongly encourage you more than I have ever before, to set the positive direction of one of your axes towards the center of curvature, no matter what the actual acceleration is. You'll understand why I'm saying it like that in just a minute, but set the positive direction of one of your coordinates towards the center of curvature. The reason is very straightforward. Only the radial acceleration is causing the change in direction. And that's the one where the acceleration is proportional to v squared over r. So you need to be able to analyze by itself the acceleration that causes centripetal motion. Now in this problem, that's very straightforward. There's only these two forces. So I'll say that the net force equals MA. I want my forces to be unbalanced to ensure my car accelerates. And I'm going to go one step further and put the C there to remind me the acceleration is due to the fact that the car is going in circular motion. Next, I'm going to do the same thing I've been doing for the last 2 weeks. I'm going to follow these instructions, which say to add up all the forces. I'm going to focus on the fact that they're unbalanced in the y direction. It's a one-dimensional problem. And I'm going to say that I have normal minus weight equals m, and I'll substitute v squared over r for my acceleration, which gives me that my normal force has this mg part, but it also has this part that deals with the fact that the car needs to have an extra amount of force to ensure that it makes this turn, that it curves out of the wash. And there's a lot of things here that I think seem obvious to me, but probably less obvious to you, that if I go faster, it's going to take more. Now, just so you know, remember, the normal force isn't just what's happening to the car. It's also what's happening to you. You're in the car. You're going the same speed as the car, which means there has to be an unbalanced force on you in order for you to travel in a circle, or else you go in a straight line and the car travels in a circle. That's going to be bad for you. So this portion is the increase in normal force necessary for you to travel in that circle. Generally, this is not the way a question in AP Physics C would ever be phrased. I'd probably ask a question like, how fast would you have to be going to experience 4 times your weight? That's probably more likely what I would ask. I'll say that again because I want you to hear what that question's like before I just spear it off and start talking about it. I would change the question. I would turn it into something that would be a little bit different and say, how fast would you have to be going in order to experience 4 times your weight? That's a much harder question because it leaves you wondering, what the heck do I do with that 4 times my weight part? And that's where you realize that for you to experience your weight, we're talking about normal force. So if I want you to find the velocity necessary for you to experience 4 times your weight, I'm asking you to say, okay, I want to know what velocity would make the normal force equal to 4 mg, 4 times your weight. And then tip the problem so that now you're solving for the velocity instead of the force. Not much of a difference, but enough to throw some students off. So first, I'll cancel out all the m's because this doesn't have anything to do with the mass, actually, which is kind of interesting. And then I'll subtract g from both sides and get 3g equals v squared over r. And then v equals the root of 3gr. You kind of know you've done this correct when you look at the units of your answer. This needs to be a velocity. So when I look under that radical, I see g times r. Well, g is meters per second squared. R is in meters. So it's the square root of meters squared per second squared. That seems to be the right kind of units. And although I'm saying this deliberately, I'll go back to, it's always easy when Mr. Shelton is doing the problems. But in my head, these are all the things that I'm doing to make sure that I'm getting the right answer, that I've done my algebra correctly, that I've not made a haphazard mistake. Now I'll stop there for this problem because this problem is good, it's nice, straightforward. And I want to point out that there's more to do, but how many of you are comfortable with this so far? All right, so that's good news. So how is it going to be different in here? Well, look, there's no reason I have to be at the bottom of the bottom there. Right, we can handle more complicated arrangements. And because of that, we can recognize that you are still in circular motion, even if your velocity may not be constant. Even in a situation like this, if you're required to figure out what's happening as you leave the wash, then you might be in a situation where you have 2 different accelerations. Now, the truth is you only have one, but you can think of it as one that's radial and one that's tangential. Because if this isn't a car and I just roll a marble down into this bowl, and I want to know what the normal force on the marble is, or I want information about the acceleration of the marble. If the marble makes it to this point in the problem, well, then looking at what's happening there, and let me let's consider just what's happening right there. I would recognize that, well, I'm going to need a coordinate system, and an appropriate coordinate system is going to have to be one that's lined up with the center of curvature. And I know that the normal force is going to have to be greater than the component of the weight in this direction. But I'm going to notice that there's a component of the weight in this direction too. That one is also unbalanced, which means I'm going to have a net force in the x direction that's equal to ma, and a net force in the y direction equal to ma. One of these is radial, and one of these is tangential, meaning one of these is making it so my car is traveling in a circular path, and one of these is speeding up or slowing down the car. That's mechanics. That's what we can do. We can do this. I wouldn't have brought it up in AP1, but I will bring it up here. Now, we're not going to do this problem right now. I'm just giving you kind of a glimpse of where I'm going to set the expectation. So let's take a look at what we should consider the very next example. And let's take our car and make it go over a hill. Whee! Now, it shouldn't have been a surprise that in the prior example, you feel heavier when you go through the bottom. But that also means that there's going to be a situation like this, where you're going to feel lighter. You know these experiences because you've been on roller coasters before. So you've had the experience when you go over the top of a hill, you feel lighter. We go through the bottom of the hill, you feel a little heavier. Well, now we should be able to show why. So the thing about this problem and why this problem is specifically different and why it's worth really talking about is the fact that in this problem, we've kind of flipped the script a little bit on where the radius is and the center of curvature is. The center of curvature is below me now. So when I look at being at the top of this hill and consider the forces that have to be acting on me, my unbalanced force has to be towards the center of the circle, which now is underneath the roadway, which suggests that the only way I can travel in a circular path is if the normal force is less than the weight, so that the unbalanced force acts downwards. The problem with that, of course, is there's a limit to how small the normal force can be. It's not like the normal force can grab onto my car and pull down. That's what roller coasters do. But in this case, I've got a functional limit. If I go at a speed fast enough to require me to need normal force that pulls down, I'm not going to get it. And the car is going to leave the roadway and go from something traveling in a circle to something traveling as a projectile. I'll still have a downward force. I'm still going to be brought to the ground, but not in a circular path, in a parabolic path. And that's probably going to be a problem for your car. So in this question, generally it's a threshold question. What is the fastest that you can safely navigate the top of the hill without the car leaving the ground? That's the way this problem tends to sound. And it still starts the same way all of these force problems start. Free body diagram, first or second law. And in this case, we know it's got to be second law. Why? We're traveling in a circular path. Only difference is that now our acceleration is prescriptively known as being based on the velocity and not the change in the speed. So we do the same things we've always been doing. We draw a free body diagram. We determine what we're going to call positive and negative. I'm making my positive direction towards the center of curvature on purpose to be deliberate. That's going to make mg positive and the normal force negative. I'm going to set that equal to m v squared over r. And then for a few moments, ponder what it means to have a threshold. In this problem, when I'm trying to ponder the idea of threshold, I recognize that the normal force is my responding force. I can't add it to this. I can only subtract it. What's the smallest the normal force can be? And the smallest it can be is 0. It can't be negative. I can't cancel out that negative sign and start adding to the weight. It just doesn't do that. Under this circumstance, the velocity to me changes to V max. It's a threshold. Can't go faster than this. When you look at this function right here, if V gets bigger, then N has to get smaller because N's a responding force. And the smallest it can get is 0. If you don't like it that way, we can always consider solving for normal force. and some of you like seeing it this way better, this is a constant. This doesn't change. And the normal force can't be negative. So I can switch this and say the normal force can't be negative, so the normal force has to be greater than that. Because it has to be a positive number. Either way, cancel out the m's, solve for Vmax, and you get yourself the square root of g times r. That's it. That's as fast as you can go. You go any faster than that, you're leaving the roadway. Anybody done it before? Yep, me too. It's not a comfortable experience. Not even a little bit. I was not prepared to leave the roadway. I did not understand physics at this moment when it happened to me last. I was 16. And I didn't want to do that anymore. Now I've done it since, but I was prepared to leave the roadway in all of those other circumstances. And I was usually on like a quad racer, or, you know, motorcycle or something like that, dirt bike. Now, a couple of things here. This problem's not particularly hard. A lot of AP Physics 1 students struggle with it. They struggle with threshold problems in general. The hardest part here is recognition of what it means to be a responding force, and understanding the parts of this problem that aren't responding, that are fixed. Your weight is fixed. Your mass is fixed. The radius of curvature is fixed. These are things that don't change in the course of a problem. When you approach the hill, the only thing that changes is the normal force. It can be changed because it responds to the situation at hand. How are we feeling on this one? All right, so those are the basics. Let's turn it up a little bit. All right, let's get a little bit better. Let's consider the light, the intersection. When you're gonna, make that turn, your car here, and you, of course, understanding the rules of the road, must turn from the leftmost lane to the leftmost lane. You understand the rules of the road. Your car is traveling at velocity v, has mass m, radius of curvature here r, coefficient of static friction s. What's the fastest you can safely navigate this turn? Now, I would love to work this problem out for you, but I've done enough talking for the time being. You're going to need to work this problem out. And I'm going to hit up a couple of you to help me work this problem through. And I'm going to try and pick on the people I think will have some difficulty in doing so. So make sure you work it out. Because when I say explain yourself, I'm going to be looking for an explanation. So let's stop the. Sure is, that's right. So that part doesn't get recorded. So in the middle of my video, it's just going to cut to me saying, sure is, that's right. Not that I watch these videos, so I'll never know. We're waiting for that other room to finally close. Come on, Sam, Jason, Rudy, let's get in here. Now I can pick on you guys. There they go. All right, so let's start. Let's see, who should I pick on at home? Sam. How you doing today, Sam?
Doing good.
Glad to hear it. Glad to hear it. Can you help me with this problem a little bit?
To an extent, yes.
To an extent, yes. That's the right answer. So could you tell me maybe where to start?
So I drew a free body diagram first.
Excellent. I love a good free body diagram. How's it look?
There's normal force pointing upwards, and
okay. So I don't want to stop too much what you're saying. You guys do understand that we have a top-down look at this, but that might not be the best way to draw our free body diagram. So a change in perspective is not bad. So let me ask you, Sam, are you drawing your free body diagram facing the back of the car, the front of the car, or the side of the car?
What? Wait, can you repeat that?
Yes. When you're drawing your free body diagram, and this represents the mass of the car, you're telling me that the normal force is up.
Right.
That's what you just said. So am I looking at the car from this angle with this being that, and that's what you're talking about? That's the side of the car. Or am I looking at the back of the car? So like this is the road, this is the tires, this is the back of the car, back of the car, you know, back of the car there. That's a car. It's a hamburger. It's a car. And it's going, say, into the page, and this is the normal force. What are we looking at here?
I'm looking at it like the back of the car.
Okay. Now you guys laugh, and I am trying to joke around a little bit. That's an important distinction. If you don't know how you're phrasing this or what direction you're looking, you really won't understand what's happening in the problem. So yeah, we have a normal force up, but we're looking from the back of the car. So the velocity is into the page. That's how we say this, into the page, because although it's not into the page, it's into the board for you guys. It should be into the page, into your notes. But we are saying the velocity is, you know, into the surface of which we're writing. That's important because we have to figure out what direction our forces act. So keep going, Sam. You're doing fantastic.
And then I put mg opposite of n.
So downwards.
Yes.
Right?
And then
Okay.
I put friction towards the radius or where you're turning, so to the left.
There it is. You're making a left-hand turn. I need my frictional force to be an unbalanced force to the left. It is friction that causes our car to turn. Your free body diagram. Fantastic. Thank you very much, Sam.
No problem.
So, Valerie, can you help me out? What do I do next?
So from there, what we did was we set up that the sum of the force is equal to M and then AC.
Okay, so next, sum of the forces equal to M, A, C.
And we know that it's in the X direction because the car's not moving up and down.
All right, so I'm going to call this the positive X direction, making these positive and negative Y direction. Okay.
And then we said F is equal to mv squared over R.
Okay. You're doing great.
You want me to keep going?
One more thing.
Okay, and then we replaced F with the coefficient of static friction times N.
Okay, I'm going to stop you there. I'm going to prefer you do this a different way. So not that what you did was necessarily wrong, but whenever we are dealing with static friction, I want our substitutions to go into the inequality. Okay, so we're going to go the other direction with it. Rather than plugging this here, my preference is for you to plug this here. It's not much of a difference, but remember, it preserves the inequality for us. And I want to keep trying to do that. So Ivan, what do I do next? He was shocked.
Hello?
Hello?
Okay, so you subbed it into the inequality, yes?
Yes, I will. M v squared over R is in my inequality, yes.
Yep. Okay, and then I replaced N with mg.
Okay, let me catch up to you. So we did net force in the Y direction equals 0, and you're replacing N with mg because they're equal. Fantastic. And there we go. So cancel out the M's.
Yep.
And what are we solving for in this problem?
Velocity.
Yeah, so let's remind us that we're solving for the velocity. So go ahead.
Okay, velocity is equal to, or not equal to, less than or equal to the square root of mu subscript s times g times r.
Perfect. This is exactly what I want you to do. Yep, this is what I want to see. So first, it preserves our inequality, which lets us know that we're not just looking at the threshold. We have to keep our velocity at this pace or less. It gives us a clear idea of what the direction of our inequality is. And I think that's, again, I'm stressing how important I find that to be, and it will be that important on your exam. But in addition to that, it tells us what our qualities are. Notice, it doesn't matter what the mass is, but it does tell us very clearly that changes in the coefficient of friction are going to make big changes in our ability to decide how fast we can go. You know, generally, the tires in the ground have a coefficient of static friction that's really high, like 0.8, 0.9. But the moment it rains, it can drop down to 0.6. That's a massive difference in what your possible speed is going into a turn. Yeah.
Can you explain why it's a coefficient of static friction instead of kinetic?
Sure. And I was really hoping that somebody would ask that question, because I don't think it's something that you should blindly accept. But we do not want the tire sliding with respect to the surface. We want the tire to stay in contact and not slide with respect to the surface, which is why it's static friction, not kinetic friction. If kinetic friction is taken over, your tires are sliding. You got to.
Because the tires are the part of the car connected to the.
Yep. At the point where the tire touches the ground, it is not moving with respect to the ground. Now, we'll be talking about rolling and rolling friction second semester. And trust me when I say, you know, rolling's a little bit complicated. There's a lot going on when things are rolling. I like this question. This is still, to me, AP Physics 1 level, but it's getting a little beyond that, but not too much beyond. So Max Shreyas, do you have something to add to this? Because I'd love to hear what you're talking about. Okay. I was just curious. You're often talking about physics stuff. Interesting you should ask. Or interesting you should say, what were you talking about when it comes to brakes? How many of you guys know how your brakes work? Or have an indication? Because they work on friction. They work specifically on friction, by the way. And if you've ever had to replace any of the brake pads themselves, like taking them off the car, put the new ones in, only one of us has this, two of us have this experience. Then once you've done it once, you really get an understanding for what's taking place with your brakes. Interesting thing about it is, you know, no matter what you do, that's going to be a part of your car that's going to wear out. It has to, because it's using friction specifically. So it's one, and it uses kinetic friction, which is why you should get a nice uniform application of a force against the tires, because you're supposed to be using kinetic friction. It's when they lock up that you have a problem. Most modern cars today have anti-lock brakes. Are you aware of whether your car has anti-lock brakes or not? They don't sell a car without it. They all have to have it now. By I assume because probably California passed the law first, but then it spread to the rest of the nation. Anti-lock brakes are pretty amazing. They are pretty amazing, but they don't make you stop sooner necessarily. They just make sure your brakes don't lock up so you don't lose traction. All right. 7th period goes so fast for me. You guys have a nice day. It was nice to see all of you today. And I will see all of you tomorrow. So, bye-bye.